Let's start. Okay, the clock is running. Okay. So thank you very much for the introduction. So you already know I'm Björn. I work for Grafana Labs. I have the proper branding in my hoodie here. I'm really glad to be here again. 5 years ago, I had a talk here, and back then I was at SoundCloud. That was already just said. So you might know me if you're a regular. We had a few people who were here for 6 times, 4 times, whatever. So you might remember me from 5 years ago. If you don't remember me from there, you might remember me from this thing, which is a low resolution logo of Prometheus. and the branding is also here. So Prometheus is an open source metrics-based monitoring and alerting system. And over the last 10 years has become the de facto standard in the cloud native space. Some of you might know this, might have used it already. And if you have seen a talk by me before, it was usually about Prometheus. But today, I don't want to talk about Prometheus. I want to talk about memory management in Go. But of course, I cannot just ignore Prometheus. We will use Prometheus as a case study because in all those years, we ran into a number of issues with memory management. And I like to bring it to this conference because, I imagine this is a conference full of C++ hackers. And they usually know a lot about memory because in C++ you are kind of closer to the metal, and you can deal with memory in a more informed way, let's say it. And it might be interesting to see how that works in Go then. Okay, Go. It's a garbage collector language. So naively, you might think I take this penalty of having a garbage collection, cost resources, might cause latency spikes, cost CPU cycles. I do this so I never have to think about memory management again, right? That's naively true. In simple cases, it just works. But of course, in practice with sufficiently complex programs, things change. And it's very easy to build a memory leak, even in a garbage collector language like Java or Go. But I'm not even talking about just memory leaks. It's more, what happens if you do serious stuff? Prometheus is kind of serious. I like to say Prometheus is not a time series database, but it has an embedded time series database. So Prometheus collects metrics, and it has to store them somewhere. Eventually, we store them on disk. But as with all things in computing, disks are horribly slow, so you want to keep as much as possible in memory. So we had this ingenious idea to represent the TSDB data in memory in a really nicely compact way. So you could call it in-memory compression. So we can have a lot of data in memory in a very specific way. And it was kind of fascinating over the years that our ideas, we weren't the only ones having those ideas. Like people at Facebook, and certainly in many other places, but at Facebook they have a in-memory time series database. I will call it TSDB from now on. They called it Gorilla back then, but I think trademark issues or something. They call it different now, but they thought a lot about it, and they published a paper, the so-called Gorilla paper, which you see linked here. It's a true classic by now, so if you're interested in those things, you should read it. And by the way, you don't have to take photos of those links. I will give you a link in the end where you can just access those slides, and then you can click directly. So this paper shared the ideas that that Facebook people had, and we realized they had a lot of similar ideas compared to the ideas we had. They just were way smarter, and they went way farther with their ideas. And then we got inspired by them and reintroduced the more radical ideas into Prometheus, and that was quite fascinating, right? It's almost like science. You come up with, from first principles, you come up with new ideas, and then you realize other people had the same ideas. And if you want to learn about that story, okay, there we are. This is a talk I gave long ago about the Prometheus 1 TSDB, and I also explained this whole story and all the details how this in-memory compression works. And then just that you know, in Prometheus 2, the TSV was completely rewritten. This one idea of in-memory compression stayed the same, but if you want to know how Prometheus actually works nowadays, then you have to watch this talk, which is by Fabian, who did the rewrite of the Prometheus TSV back then. It's also a classic by now. So just all references so you know how it really works. I don't want to talk about this here, I just want to talk about how we manage this memory. So in a garbage collector language, you put all those things on the heap, right? So you don't have an explicit malloc call or something, you just create a slice. I mean, in Go, arrays are a bit special, and we usually call them slices, although they are not really arrays. So you just create slices of bytes, and these are memory, pieces of memory that you could use, and they are managed by the garbage collector. And in Prometheus, we thought, okay, if you have a 64 gigabyte machine, so you should definitely use, let's say, half of it for caching those TSV data chunks. And if you do this, you will realize that you will still run out of memory. So you oom, right? I don't know if that's a common thing. I call it ooming. So your Prometheus processor will just run out of memory, although you have twice as much memory as you have reserved for the caching. Of course, Prometheus is doing its own little thing, the normal stuff that it uses memory for, but somehow that feels like a waste. Maybe Go is super inefficient with this memory management, and you need twice as much memory as you actually thought. And to understand this, you have to check how the garbage collector in Go works. There is a very nice document with all the details. You will see I give a lot of links to further reading, so you can always drill down into the details if you want to. And this page has a really nice feature. It has interactive graphics. And I was tempted to do this live here on stage, and you can like move those parameters and then the graphic will change, but never challenge the demo gods, so I thought I'd just take screenshots, but you can totally go to this website and play with those graphics. This graphic is really nice. It explains how the garbage collector is triggered. The garbage collector isn't just running all the time, it has garbage collection runs, and they need to be triggered at some point. Oh no. I can still see the, okay, here we are. So the very simple, Go is all about simplicity. They try to make it all very simple. So there's just a single knob you can turn, which is GOGC. We will talk about it in a second. In Java, you might remember there are a lot of little settings for the garbage collector. But they try to get away with just one knob. And what it does by default is it always waits for the heap to grow by a factor of 2. Like double the heap and then start a garbage collection. And this graphic shows you that the dark blue one is what's remaining after garbage collection, and the light blue one is the actual heap size. So in the beginning, your program starts, uses some memory, and then I think this is 4 megabytes where it starts for the first time, but nothing is garbage collected, so it does more. And at 8 megabytes, you try again, but nothing really is garbage collected. You go to 16, well, maybe there's a little dent. But then at 32, you garbage collect actually something. And then you end up at 20, so you go up to 40, you trigger garbage collection. And this seems to be the steady state here. So you get this sawtooth pattern. That's very typical for a Go, like a Go program, how it uses its memory. And you see peak live memory is 20 megabytes, that the actual peak memory is twice as much, which seems wasteful, but it also already requires a lot of CPU power for the garbage collector. And there's a trade-off, like always in engineering, there are trade-offs. And of course, you don't want to waste too much CPU to save memory and vice versa. And the default idea, the heuristics is here, okay, I just garbage collect whenever my heap has grown to twice the size. And that's encoded in this GOGC setting, which is a environment variable you could set, but you can also tweak this within your program. The default value is 100, which means grow by 100%, which is factor 2, right? And then start a garbage collection. So this can also, you can set this to any number, which is kind of a percentage. You can set it to off if you never want to garbage collect. Sometimes you don't do a lot of dynamic memory allocations, or the program doesn't run very long, and so why not? But of course, if we have this case in Prometheus where we have gigabytes of memory we're using for the TSDB in memory, and we don't want to waste twice as much, then we are tempted to tweak this, right? So let's say we set this to 40, which means I only let the heap grow for by 40%, and then I do a garbage collection. And in this example, whatever, life of a program here, you see you get way more frequent garbage collection cycles. You only get 28 megabyte peak, which sounds much better, but you also waste 13.9% waste. I mean, the garbage collector just takes that much, right? So it's a trade-off. The thing with Prometheus was that this is like a few garbage collection per second, but with Prometheus we saw garbage collection was almost never happening. It was like happening once per hour or something. And why is that? That's because we stored so much, let's call it static data in memory. So Prometheus collects metrics data, puts them in a nicely compressed way into RAM, and this data is so nicely compressed that you can store hours, days, weeks of metrics data in memory. It will never be touched. I mean, it will be read when you run a query, but it will never, like, you don't allocate new memory and free it. And so the garbage collector didn't have a lot to do, and you would see very infrequent garbage collection cycles. So for Prometheus, this setting was actually really, really good because we didn't have like 13.9% for garbage collection. We had almost nothing. So we were kind of not doing garbage collection and wasting a lot of memory. So we really had to tweak this. And this is like code archaeology. It's like ancient Prometheus version 1 code. And you can see in this comment, it's explained why we set this to 40. And here you can also see how you set it from within your program. Funny enough, it's in the debug package. Don't ask me why. So debug.setcgc%, and then you set it to whatever you want. And we even check out if the environment variable is set, because the users could still tweak it differently if they want to. They might have a different usage pattern of their Prometheus server. So we check, is the environment variable set? And if yes, we let the Go runtime do its thing. And if it's not set, then we set it in the program. And that worked quite nicely, right? So that was a huge win for Prometheus. We don't waste half of our memory anymore. But we needed a tweak. But that's not everything, right? So we don't keep everything in RAM. The Gorilla thing, that is really like completely in RAM. But with Prometheus, you usually at some point you have collected more data than fits into RAM. We want to persist it to disk anyway, but also what happens if you have more data than you fit in RAM and you have it somewhere on disk, but then a query comes along and wants to inspect this data that is just on disk and not in memory. So we had to implement some memory management on our own. I mean, you could argue we just add more swap space, right? That's what you can do with modern operating systems, right? You just add gigabytes and gigabytes of swap space and let the operating system do its tricks. But most of you probably know if the machine starts to swap, all bad things happen. So that wasn't really what we wanted. So we started to write code that identifies the part of the TSDB that haven't really been accessed in a while, and when we run out of RAM, we evict those things. We have written them to disk already. And when a query wants some data that is only on disk, we have to identify that data, we have to find it on disk and load it back in. So there could be whole talks, those TSDB talks that I linked in the beginning, they talked also about this, how you do this, how you write it to disk efficiently, and how it was not very efficient in Prometheus 1 and way more efficient in Prometheus 2, and so on. But for us, it's only important that there is logic to know, there is logic to identify data that can be evicted from memory, and that there's logic to find data on disk and swap it back in, for lack of a better word. There's one problem though. In Go, you really don't have a way to find out how much memory pressure do we have on the system. You can measure how large your heap is, and you can use that as an input. But then we have to ask the user, what heap size do you want? And that is a very infamous Prometheus 1 command line flag, because most people just naively start a program. They don't think about setting a heap size. And that's the default value. It's 2 gigabytes, which is kind of fine on a small process, on a small machine. If you just start a test run on your laptop, that's why we used it as a default. But if you have a giant machine and you want to use all the memory for your TSDB buffering, then you have to tell Prometheus, and that's not very obvious. So people got hit by surprise by that, and we really didn't like that command line flag. I guess it's not that bad in modern cloud deployments where you have to ask Kubernetes for some memory reservation anyway, so you know how big your memory should grow. But yeah, it wasn't great, but it worked. So good enough for now, right? If we fast forward, I mean, this is Prometheus 1. We are talking about the year 2015 or something. Just last year, Go introduced a second knob for the memory management, for the garbage collector in Go 1.19. And this is about solving a slightly different problem. So this is, again, from this document, Interactive Graphics. That's a case where, not like Prometheus, where we have a lot of huge static data on the heap. This is about something where a program has a very short spike in heap size. And of course, because of this 100% growth, you get a spike twice as large, and you only have the spike, whatever, once in a blue moon, and you need to reserve enough memory for that to work. And that's also annoying. You would like to run the garbage collector very quickly here, but not as quickly here where you don't really need it. And that's a problem. That used to be a problem in many Go programs. If you are nowhere close to the memory you actually have available, you would run the garbage collector too quickly. And if you get close to it, you would run it too slowly. So next knob here is, it's called memory limit here, but it's also an environment variable, GOMEMLIMIT. I don't know why they called this GOGC, and they should have called this GOMEMLIMIT. And you can set it to whatever you want. By default, there's no memory limit, and it's the old behavior. And if you set it, it's a combination. So you would still do this 100% growth and start to garbage collect, but if you get close to this memory limit, you start to garbage collect really quickly. So this is pretty static, steady state here. So that's not so interesting, but it gets interesting if you really switch it completely off. Like I said, you can switch off garbage collection, but if you set a memory limit, you will still garbage collect, but only if you need it because of your memory limit. So no garbage collection happening, and only here where you get close to it, you start. That might be pretty cool if you know how much memory you have available. But this is the case where you handle this memory, this heap peak, right? So small garbage collection cycles here, quicker here, and then slow garbage collection cycles here again, which is pretty much, this is what you want. The only problem is now you have to tell, the user has to tell how much memory there is, which again, in a cloud deployment might be just what you do anyway. And this is nicely aligned with what we did in Prometheus 1, right? Where we asked the user, how much heap do you want to give us? And so if we did Prometheus 1, this year or last year, we would probably use the GOMEMLIMIT and set it to just something slightly larger than what the users wants to give us for the heap. So if we do I don't know, rewrite history, yes, that might be something to do. In reality, of course, it's all more complicated. You cannot just start the garbage collector when you hit the memory limit. That might be too late because the garbage collector takes a while, and while it runs, new memory gets allocated. So in reality, there's a GOGC pacer, which is horrifically complicated. And if you want to know all the details, there was a GopherCon talk last year, which is really, really deep. So it's an hour of a talk just about this. I couldn't replicate that. So again, you get a link to watch it if you want to dive deep into this. Okay, but let's go back to Prometheus. So Prometheus 1, let's imagine we have the GOMEMLIMIT. So is this what we want? Do we happily live ever after? Not really. I already said we are annoyed by this, that you still have to ask the user how much memory you want. And there's all this complexity of us deciding which part of memory don't we need anymore and move them to disk. And if something is on disk but not in memory, we have to swap it in. And it sounded really like this is something the operating system should do. The operating system is probably way better in that. And also, because we already had compressed the data in memory, we could just mirror it one-on-one onto disk. We didn't need additional disk compression. It was already compressed in a nice way. So we kind of mapped data on disk to data in memory, and it really sounded like, all the C++ hackers will already want to scream at me. There's a syscall for that, right? And the syscall is called Mmap. So you can look it up in the Linux man pages. So why aren't we using that syscall, right? We were asking that ourselves, and in Prometheus 2 we decided, yeah, let's use mmapping. That's the best thing to do. The problem is just it's a syscall, so it's literally a C function that you call, and Go is not C, right? But surely there will be something in the Go standard library to do mmapping, right? But Mmap, no mmapping in the Go standard library, which it should have raised some suspicions, I guess, that we might do something weird, but we'll come to that later. I mean, the Go standard library does something like reading stuff from the network, reading stuff from a file, which are under the hood all syscalls, right? Just that you don't do syscalls directly. It's like wrapped by the standard library, which is also cool because syscalls aren't very portable. They might be more or less the same on different Unix flavors, but also it depends. But they're completely different on something like Microsoft Windows. So how to even do syscalls in Go if you want to do them on your own. So there's no mmap support in the standard library. So we have to do syscalls on our own, not using the standard library. So for that, because syscalls are platform dependent, you need platform dependent code. And I mean, Go is supposed to be portable, but it supports little pieces of platform dependent code. And there are two notions in Go: the operating system you run on and the architecture. And there's a Go OS setting or environment variable for the operating system and from the architecture, and you can run Go version to see the values that are on your platform. So I run this on my laptop, I get Linux AMD 64. If my laptop was running Windows, it would get Windows AMD 64. But if it's on Apple and it's an M1 architecture, you get like, I don't know, I guess it's Darwin or something, and I don't know what the magic string for M1 is. Those, you can set those environment variables actually, and then the Go compiler will just cross-compile for that. Cross-compilation is super easy in Go, so that's all really cool. But you can use those magic words as suffixes in file names. It's really confusing if you do this by accident, and then suddenly this file is only compiled on Windows, where Go OS is Windows. This, you would think this is only compiled on Unix, but I'll come to that. So this is, by the way, this is now real Prometheus 2 code, github.com Prometheus. TSV file util contains stuff how we deal with files, and if you check files that start with mmap, you get those, right? So they're for different architectures, different operating systems. And this is the one that is always compiled, and it has the platform independent code. And I mean, these look bigger than they are because most of it is just the Apache 2 license header. So they usually are just a few lines. Just Windows, of course, needs more code, as usual. Okay, so this is platform-dependent code, and we'll look into the Unix file in a second because it's the simplest one. And Unix, by the way, is not one of those magic strings. So on Linux, it's Linux, and I guess on BSD, it's BSD or something, right? So Unix actually is always compiled. It's not one of those magic strings, but you can have build tags. That's a build tag. So this is the Unix, the mmap_unix.go file, and it's only compiled if it's not Windows and not Plan 9. Plan 9 is like a weird operating system run by Rob Pike, who also created Go, so Go supports it. JS, what is JS? It's WASM, right? WebAssembly. Go can also compile towards WebAssembly. So in all those cases, don't use this file. And then confusingly, you have the same thing written again in a slightly different syntax. That's just the old until Go 1.16, and then they created a more powerful syntax, and you can write both if you really want to be super compatible. But in modern Go, you only need this build tag. So this is only compiled on essentially Unix, like not Windows, not Plan 9, not JavaScript. And luckily, the mmap syscall looks the same. And then you need this weird package. It's hosted by golang.org, so it's kind of a Go package, but it's not part of the standard library and has all the bindings for Unix syscalls. And this is how you call them, like unix.mmap. And here you see this is pretty much just essentially the C function prototype transformed into a Go function, but we wrap it so that we into a function we call mmap, and we can do it differently for Windows and other platforms. It's just more complicated, but in the end we have like an mmap call that we can always call, And that's how it looks like. You give it a file pointer, you say how many bytes you want to mmap, and then you get a byte slice back. So usually this would be something on the heap, but in this case, it's just like you use this byte slice to access memory that is mmapped towards a file by the operating system. It's not on the heap, and you just use it as if it were in memory, and the operating system will magically make sure if it has to be loaded from the file, it will do it. And it will evict it from memory if you need the memory for something else. So very cool. This works. So we have no heap allocations for our TSDB bulk data. We don't need to treat the garbage collector anymore. We don't need to ask the user for any memory size because that's what the operating system is doing really nicely. It just gives us all the memory that the machine currently has. So we can just buffer, and when the machine decides I need the memory for another process or your own process is doing something else with the memory, it will just clean this memory up. It will just be on disk, and it's all great, right? So they lived happily ever after, right? Kind of. I mean, this works really well, and Prometheus 2 is now 6 years ago that we released it. We never changed anything fundamentally about it. On the contrary, we even mmap more stuff, like their mmapping is just like a drug. It gets you, it's all magic and it's cool. But maybe sometimes not. So it works well, but if you run Prometheus under more extreme circumstances, you might run into problems. Now, mmapping has a lot of problems. You can search the internet for mmap problems, right? And then very prominently, you get Linus Torvalds yelling at you how you're using mmapping in the wrong way. I'm not talking about those general problems. There are general problems with mmapping. I'm talking about a problem that is very specific to Go, and this is why I thought it might be nice here at the conference, because it might come as a big surprise if you just use Go and you think the mmapping is just the greatest thing ever. And it might also tell you why it's not in the standard library. So one of the extreme cases of using Prometheus is if you take it apart, Frankenstein's monster approach, and turn it into distributed systems where you have many little microservices that you can scale horizontally. And that's essentially what the Mmap project did, also some others. But my employer, Grafana Labs, they are running a kind of Prometheus as a service thing, which other vendors are also doing. Some of them have just programmed it from scratch to implement the Prometheus API. Some have just used the existing distributed TSDB and created a layer on top, so it's compatible with Prometheus. But Mimir is essentially taking literally the Prometheus code base, taking it apart and creating some kind of distributed system from it. And one of those little components is the store gateway, and it uses Prometheus code, so it uses the memory mapping, a dedicated service in Mimir that is responsible for fetching metric data from the object storage. Of course, you don't have disk, you have object storage in the distributed systems. All those things, right? So this is a blog post from earlier last year by my colleague Charles, who found out the reason of a problem we ran into. And the problem was weird latency spikes. All of a sudden, this store gateway would essentially block completely for, 50 milliseconds, 100 milliseconds. And that's really bad if you have like really tight SLOs and you don't want your store gateway to just clog up and then all your customers get nothing for, 100 milliseconds. But why? It was so hard to find out. And in the end, they found the culprit, and it was, no surprise here, it was mmapping. So what they did for the store gateway, they kicked mmapping out of it again and did all the stuff that we did in ancient history. So now you manually decide, okay, I have to load this data from this. You just open the file as usual via the Go standard library, you read the data in, and if you realize there's too much data in memory, you have to decide again which part you don't need anymore and you can free up. But why? And that's what I would like to talk about in the last, 10 minutes we have. For that, to understand what's happening here, you have to go down into the Go scheduler. And the Go scheduler is really interesting. And Go has a few, design priorities. And I think the most important one is simplicity. That's why they had only one knob for the garbage collector and then very reluctantly add another one when Go was like 15 years old or something. Another thing that is very important for Go is very, very nice support for concurrency. And one of the ideas was that whatever. Let's call them threads. They should be super lightweight. And actually, I mean, an OS thread, which you might know as a lightweight process, it was already too heavyweight in the modern concurrent world. You might run thousands of, let's call them threads in a program, or I have seen 1 million. And if you start 1 million OS threads, your machine will probably die. But you can start 1 million Go routines, and Go routines is the lightweight thread that Go supports. It's really easy to start. And the trick how they accomplish that a Go routine is so lightweight, that's kind of here in a very simplified form. Again, there are nice documentations on the Go website, or you can just dig into the code. It's all open source. And there are 3 things that are modeled in the Go runtime. G's, M's, and P's. They are deliberately not spelled out, but you can imagine what they are. G is pretty much Go routine. So every Go routine gets one of those G structures in the runtime. And there might be very many of them. And only some of them are running. The scheduler of the Go runtime lets them run. And ultimately, they run on real CPUs, right? This is a very weird machine, has only 3 CPUs, but I didn't want to draw more. And then there are operating system threads, of course, and the operating system lets threads run on real CPUs. For the Go runtime, an operating thread is modeled by an M machine, I don't know, maybe. And the mapping layer essentially is P, which might be processor, probably processor, virtual CPUs. And there are very few Ps. There's actually, again, an environment variable to tweak it, Go maxprox, which by default is set to, originally in Go the default was 1. It was a bit like our 2 GB default in Prometheus. It was like a safe default, but people wanted to use more processors. So now it's set by default to the number of physical cores. I guess in a container environment, it's really what you have reserved as cores. But yeah, not a lot, right? Machine, M's, machine threads, OS threads, there might be more, but there will be just enough to saturate the CPUs. So maybe a few more than you have CPUs, but not a lot. Well, Go routine, whatever, the sky's the limit, right? And the Go scheduler takes always a Go routine and maps it to an M via this P. And at most, P Go routines are running. So that works nicely. And the ingenuity is happening when an OS thread is stuck in a syscall. That happens all the time, right? So this Go routine wants to read from a file. So you have a Go function that calls read from a file. And under the hood, it's mapped into a syscall. This Go routine is running on this P, which is running on this M. This OS thread goes into the syscall and starts to wait for data from disk. And on modern hardware, the CPU doesn't have to touch every single byte when it comes from the disk. There's like direct access, whatever. So this actually doesn't really need CPU. And the OS will happily use a real CPU to run another thread. That's what the OS is doing. And the Go runtime will also do something, right? It knows this Go routine is now in a syscall. So let's start another Go routine that is waiting for CPU time. Give it the P, it will run on a different M. And we will utilize all the CPUs nicely. Everyone is happy, right? So this is how it works, and that's essentially how you can run whatever, thousands or millions of Go routine on maybe 5 machine threads and still utilize your machine pretty nicely. That's the whole idea. Great, right? So, but now let's talk about M-mapping. So M-mapping, the syscall happened long ago, right? You M-map the file and you're done with it. And if you access this piece of memory that is mapped to the file and the data is actually not really in memory, then the operating system has to page it in. And for that, it's using something called a major page fault, which is also what happens if you do like swap space and you need to swap in data. So there's a bit of a connection to the swap thing that nobody would ever do. So a feature of this is that the user space doesn't notice. The user space notices, of course, because it takes so long, but there's no like code path that is taken. You just access a byte slice in Go, right? And all of a sudden, the operating system says, no, I have to swap this in. This machine thread is stuck. That's not new. That's not different from the syscall thing. but the Go runtime doesn't see anything, right? It's completely transparent. So this means this P will stop working, the Go routine will stop working, and the Go runtime can do nothing about it. So you have knocked out a P, essentially, for whatever, 20 milliseconds, 100 milliseconds, however long it takes to page in this data. And then, of course, worst case, 2 other Go routines are also accessing data that is currently not in memory, but is memory mapped. And then they are all blocked, and your whole Go runtime will stop working for whatever it takes. And that's the latency spike that my colleagues have seen in the store gateway. And yeah, the whole concurrency model of the Go runtime essentially stops working here. It worked so nicely before, but with the mapping and this load, like it's a feature that is transparent. You cannot intervene. And that's why some people say never use mapping in Go. And maybe that's why it's not in the standard library. So Prometheus 3, which might come out next year, we are planning for that. Maybe we kick out mapping and repeat history and write our own little mapping layer in Go. Maybe, I mean, I don't know, it will happen very soon because it works quite well in practice, just not in those extreme cases. But yeah, if you write a Go program and you do mapping, think twice. A, if it's really needed, and B, maybe you're in a situation where you run into this problem. There's one workaround where you can increase Go max procs to way more, so you can sustain more of these Ps being blocked. But that's kind of defeating the purpose of this whole contraption here, because a lot of Ps create scheduling overhead, and yeah, I mean, then you pay for it in other ways. Anyway, this is a GitHub repo where this is my GitHub account, and in this talks repo, you see all my talks linked, including this one already in the 2023 chapter, and you can see a link to these slides, so you can look up all those links if you're interested in more details. But yeah, that's it. We have a few minutes for questions. Thank you very much.
Thank you very much, Björn. You definitely inspired me to look for similarities in my language and to learn how garbage collection works there. Okay, we have a few minutes, so are there any questions? Please raise your hands here. Let's wait for a mic.
Hi. Have you considered modifying the Go scheduler in some way?
Yeah, good question. I think that was audible for everyone, right? So yeah, I mean, it's all open source. Why we could create a bespoke Go scheduler just for Prometheus? No. I mean, the one answer is it works in Prometheus too, right? I mean, that will be. I mean, it's always about trade-off, and it works fine. So maybe we don't really have a problem here. I think going down into the Go scheduler would probably be even more a rabbit hole than just writing your own. Like I mean, the good answer is, what did my colleagues do in Grafana with the store gateway, right? They just wrote this memory mapping, essentially recreating memory mapping, but in Go user space. And I think that's a more reasonable approach than modifying the Go scheduler. I mean, the Go scheduler is written by so smart people. I mean, Go is very opinionated, and there are people who just think it's all wrong, like the whole approach is wrong, and maybe they are right in certain circumstances, but I don't think that we could just make a better solution for that. I don't think we should rewrite the Go scheduler just to make memory mapping less dangerous.